Hello everyone, this is the part 5 in our video playlist, and in this video we're going to perform a von Neumann stability analysis of the Crank Nicolson method used in part 4 to prove that there is indeed no constraint on the choice of dfx and dft with regards to stability. So previously we did the same thing with our explicit differentiating method, so now we're going to do the same von Neumann stability analysis for the Crank Nicolson, which is the implicit differentiating method, right? Okay, so previously we determined this equation for the Crank implicit differentiating method, right? So we're going to need this equation. So I can copy it down here. I'm going to paste it. So I'm going to use this equation where our u was equal to, it was equal to alpha times delta t. It is alpha times delta t over 2 times delta x squared. Okay? So, and we said that our temperature at J at times equal to n is going to be equal to the e to the I times k times j delta x, right? And our times I times k squared and delta t. So that's how we express. So in our von Neumann stability analysis, that's how we express the temperature at a particular time at a particular section of our bar. So our temperature at J plus 1 at a current time is going to become e to the I k J plus 1 delta x times the e to the I k squared and delta t. So, which means our temperature at J plus 1, we can express it as in terms of Tj and n, right? So we can express all the variables in terms of t at a current time and at a specific region. Okay, so that's going to be Tj e times, so it's going to differ by the term of e to the k delta x. Yeah, so times Tj at n, right? Okay, so and Tj minus 1 is going to be the same but with a negative term of it. So now we can write down the equation by factorizing the Tj at a time n. Okay, so that's going to be our right hand side, right? So but the temperatures on the right hand side are going to be dependent on, so it's going to be the same thing, but instead of at a current time, we're going to use at a later time. Okay, so we don't need the variable u is time. Okay, so I'm going to factorize Tj at n plus 1, so which becomes, this is Tj plus 1, right? So it's going to become negative u e to the I k delta x plus 1 plus 2u minus u, and this is Tj at j minus 1, right? So it's gonna be different by the factor of negative I k delta x. So that's my left hand side. So my right hand side is going to be equal to, I'm going to factorize Tj at a current time. So is that going to be Tj plus 1, so u times e to the I k delta x, right? Plus 1 minus 2u, and then plus u, but it's going to differ by the factor of negative ik delta x, right? So if I remove this to my right hand side to make my temperature at a later time as a subject of my equation, I'm going to have Tj at a later time is equal to Tj at a current time. So this thing divided by the term that I circled. So it's going to be negative u e to the I k delta x plus 1 plus 2u minus u times e negative I k delta x. So we also know that e to the I k delta x plus e to the I negative I k delta x is going to become 2 cosine of k delta x. So using this equation, my Tj at a later time is going to be equal to 2u of cosine k delta x plus 1 minus 2u. So for the numerator, that's going to be 1 plus 2u minus 2u cosine of k delta x. Okay, so we're basically working with something inside of the parentheses. So if I want to manipulate them so that kind of change how it looks, so can I try to factorize u from the equation so that it's going to become, maybe if we can factorize 2u, that's going to become cosine of k delta x minus 1, and term here is going to become 1 plus 2u 1 minus cosine of k delta x, right? Okay, so if I change this to negative, I can switch the order of something inside of my parentheses, right? K delta x. So it's going to become this. So now I can just say that my 2u 1 minus cosine of k delta x is equal to omega. Let's say that. Okay, so if I rewrite my equation with a new variable, it's going to become 1 minus omega 1 plus omega, right? So we want to show that this thing that is being multiplied with Tj at a current time is less than 1, right? Okay, let's see what our omega is equal. So the cosine is going to range between negative 1 and 1, right? So if we subtract that number from 1, we're going to either have 0 or a positive number, right? So which means our omega is greater or equal to 0. So if we consider that fact to apply to our fraction, if we subtract a positive number which is greater than 0 from 1 and divide that by a number which is 1 plus that number, it is definitely gonna be smaller than 1 all the time. So no matter what we choose for our k value to be, so which means our k is independent. So this idea proves that our one Neumann stability analysis proves that Crank Nicolson method used to find the temperature profile of our bar is constrained on the choice of dx and dt regardless of stability. Okay, thanks for your attention.